Hey everyone. In this video, we're going to take a look at reactions between acids that contain hydrogen and bases that contain hydroxide. We're going to give specific names to these types of acids very soon, but for now we're just going to talk about them in terms of containing H for acids and OH minus for bases. Sorry, H plus for acids, OH minus for bases. All right, so this is an example of the sort of problem that you would be asked to do. So we're going to start by converting these names to formulas. So we've got iron 2 hydroxide. So remember, that's Fe with a 2 plus. Hydroxide is OH that's minus. So there's two of them. We're told it's a solid. Also, if you go look this up on any solubility table or a list of solubility rules, you'll see that this compound is insoluble in water. And we're going to react that with hydrobromic acid. Remember, the hydro prefix here means that we're dealing with an acid that has an anion that is not a polyatomic. Always feels backwards because the hydro means not polyatomic. That means monatomic. So that's going to be Hbr. And it's a solution, which is all we're used to dealing with acids anyway, so that's going to be aqueous. Every time we have this combination of a hydrogen-containing acid and a hydroxide-containing base, every time that's going to form water, all right, H2O. You can think of that as an H plus ion and an OH minus ion. You can sort of think of it in an ionic way like HOH, but it's not exactly what happens. But if that helps you think about that for now, that's okay. We would just never write it that way. We'd always write it as H2O, putting the two H's together. Anyway, water is a liquid. And then you're going to have another compound that's going to contain whatever the other ions are that are floating around. In this case, you've got iron and bromine. So you've got Fe, which is in a 2 plus state. Bromine is always 1 minus, so we need two of those. And then we go check our solubility table, and it turns out that compound is water soluble, so we're going to write that as AQ. Something that people ask a lot about is how do I get that? It's just from our solubility table. We go look that up and see if it's soluble or not. There's lots of water floating around because the hydrobromic acid is an aqueous solution, so it's mostly water with some Hbr dissolved in it. So there's lots of water floating around. The iron bromide that gets produced over here on the product side is going to be have plenty of water to dissolve in, so it will because it's soluble. All right, so now we're going to go through and apply solubility rules. So remember, this first reaction, we call this the full reaction. Now we're going to write the full ionic reaction where we dissociate things that need to be dissociated. This first one is a solid ionic compound. Solid ionic compounds don't dissociate. We can also think of it as a weak base. Either way you want to think about it, it won't dissociate, right? Both weak acids and weak bases don't dissociate. The difference is the weak bases are always going to be solids. Hbr is a strong acid. How do we know that? There's a short list of strong acids. I work always with 6 strong acids: HCl, HBr, HI, HNO3, HClO4, H2SO4, and everything else is weak. Lots of people like to argue about exactly what belongs on that list of strong acids. We're going to stick with those 6. All right. So because it's a strong acid, it's going to dissociate. This also takes a little while to remember, but remember, it's that dissociation that creates these free hydrogen ions that make the strong acids strong, right? It's those free hydrogen ions that make something acidic. Strong acid produce lots of them, and that's why we call them strong, all right? The cutesy way I remember it when I forget is that the strong are willing to go out on their own. The weak always stay together, okay? So that's kind of silly and not really the most chemically accurate, but if that helps you, great. All right, so that's going to make H2O liquid, and then we've got a soluble ionic compound over here. So that's going to separate or dissociate into ions. All right. Now to write the net ionic, we always just use the full ionic and look for spectators. So what are our spectators? Our spectator is going to be those things that have the same charge and state on both sides. In this case, the only thing is bromine. Br minus over here, Br minus over here, aqueous, aqueous. Okay. Notice that the iron hydroxide, the iron on the product side is now separated. It's dissolved in water. Whereas over here on the reactant side, it was part of a solid compound. So that's definitely a change. We're going to keep that in. All right. All right. So now we're going to write what we've got left as our net ionic. So we've got Fe OH2 solid plus H plus aqueous yields H2O liquid plus Fe2 plus. All right. If you've watched the other video, you know on precipitation reactions, you know that I'm not big on balancing as I go. I like to do it at the end. If you prefer to balance as you go, that's totally fine. Just keep track of where things belong and make sure you're using coefficients and not subscripts for numbers. But in this case, you'll notice that you've got 2 hydroxides here that have got to get turned into waters over here. So for every 2 hydroxides, you need 2 H pluses, and that's going to generate 2 waters. All right. And that's it. That's your net ionic reaction equation. That's complete. It is balanced. It's got everything we need. So the process is always going to be the same. You're going to write out the reaction. If you've got a hydrogen and a hydroxide containing compound, water is always one of the products, right? And there's a compound containing the rest of the ions. Then we apply solubility rules, remembering that strong acids and strong bases dissociate, weak acids and weak bases do not. Then we cross out spectators, all right? Okay, so what I'm going to do is I'm going to give you another example, and I'd like you to, after I provide the example, I'd like you to pause the video and try to work it on your own, all right? So another example. A solution of hydrofluoric acid is added to a solution of potassium hydroxide. All right, so pause the video, try to work it out, and then restart the video to hear my solution. Okay, so hopefully you've had a chance now to work that out. So hydrofluoric is going to be HF, potassium hydroxide. K is a group 1, it's always +1. Hydroxide is -1, so that's already neutral. We're told it's a solution. You know, I think it's always good to, glance back at your solubility tables and, verify that. But assuming that the person writing the questions did it correctly, those should match up. Okay, so anyway, it's aqueous. So you've got a hydrogen-containing acid, a hydroxide-containing base. It's always going to make water. And then a compound containing the ions that are left over, which in this case is K plus and F minus. This is a soluble ionic compound. One of the things that you should notice from looking at solubility tables, or some of you may have memorized solubility rules. If it's got potassium in it or any other group 1 ion, lithium, sodium, rubidium, that's always going to be soluble in water. Those compounds are, the reason we use those compounds in lab a lot is because they dissolve nicely in water, right? All right, so now we're going to apply our solubility rules or rules of dissociation. Hydrofluoric acid is a weak acid. People get confused on this because HCl and HBr and HI are all strong. HF is the weird one in that group, so it's weak. So the weak acids do not dissociate, okay? They remain associated. So that's going to stay together. Now we've got a soluble ionic compound, also known in this case as a strong base because it's got hydroxide and it's soluble. Either way, whichever way you want to think about it, strong base, soluble ionic, doesn't matter. Either way, it's going to dissociate, all right? we've got water, and we've got a soluble ionic compound, so it dissociates like that. Our only spectator here is K+. Group 1 ions are always spectators. They don't form insoluble compounds with anything. So then we bring down what we've got left, which is HF plus OH minus yields H2O liquid plus F minus aqueous. Okay, and that is our net ionic reaction equation for this process. Oops. Net ionic, oh, come on. Net ionic reaction equation. All right. All right, I hope that that's helpful, and please add questions in the comments, and